electric field in the case of a continuous charge distribution. In the videos before, we talked about a point charge. If we take here a positive charge, Q positive, this this charge is considered as a point. To calculate the field created by this charge at any point, we can say P is equal, first of all, we can join the center of this point to the location P. And the field must be out. If Q is negative, the field will be in. Okay? And in this case, the created electric field equal K times the charge Q divided by the distance between the charge and the point P square. This is the distance. So this equation, okay, we can take it in a special direction. This equation is used only in the case of a dimensionless charged object, which is located at a distance, identified distance r. Now, in our case, we are talking about a continuous object. So this object has dimensions. First of all, we cannot use this equation because we cannot identify the distance between this point P and the object. We have many distance. We have the distance to this point and the distance to this point and to this point. All these values are different. Here we have R1, here R2, and so on. So we cannot identify this value. Which one can we take from here? The only method to calculate the electric field is to divide this object into small elements like this one. This element is dimensionless. And in this case, if we want to calculate the field at the point P, which is located at a distance r from this element, which is charged dq, the field created by dq at the point P is dE, which is equal K times the charge inside the small object divided by the distance square. We can use this equation now because the small object here is dimensionless. So we have now, we can say, first of all, the total electric field E created by a charge Q. Q is the total charge of the object. the total electric field E created by Q can be calculated by the integration of delta E. If we integrate delta E, we get the total field E. E equal the integration of delta E, which is equal delta E equal K dq divided by the distance square. As vector, we can take the vector in a special direction. Delta E also has two components. It has EX and EY. For example, we can take this case. If we draw X and Y, here we have Y-axis and X-axis, and we can draw the Y component and X component of delta E. You can say delta D, dE, small quantity of electric field. Okay, now the question, how can we calculate E? K is a constant. We can calculate, I give you its value. R is the distance. We can calculate R geometrically. So we have to calculate dq. Okay? To calculate dq, we have to talk about the charge densities. Charge densities, each charge density depends on the form of the object. I mean, first of all, if we have a charge is distributed along a line, for example, the object has only one dimension with a length L and without thickness, only one dimension L. This line has a total charge Q. In this case, the linear charge density of this object is equal to lambda. This lambda equal the total charge divided by the length of this object. The unit is Coulomb divided by meter. Now, as you see, this object, it can be like this, for example, or like this, or like this. Any shape we can take, but this object must be must has a one dimension. Let's take the second case. When a charge is distributed over a surface area, like a paper. If we take a paper, this paper has a length small a, height or width small b. We can say hey, a and b, and with area equal to a. And this object has q, capital Q charge. The area of this object equal a times b. When we have an object like this, we talk about the surface charge density sigma. sigma is equal Q over A. The unit is Coulomb divided by meter square. Okay, now we talk about the object in the form of a volume. If we have a volume, for example, this volume, it can be a sphere, it can be a cube, for example, any volume. In this case, the charge is distributed inside a volume. To calculate the volume charge density, this value, the volume charge density rho. Rho equal Q divided by the volume. This volume has a total charge Q. This volume has a total volume V equal 4 over 3 pi r cube. The unit of the volume charge density is Coulomb divided by meter cube. So Q equal rho times V. Okay, we have these cases. Let's resume here these equations. First of all, Q equal lambda L. The second case, this is in the case of a linear shape. The second case, Q equal sigma A in the case of a surface. And the third case, Q equal rho times V in the case of volume. Let's take the example. Here we have this shape, and here we have this one as a paper, and here we have a you can say cube, or you can say sphere. And before, we have to calculate E, which is equal to K integral dq divided by r square in the direction of the unit vector r. Okay, the application, we see the application later. Now, just I want to calculate dq. If the total charge is equal to q, and q equal lambda L, a small, we can see the small charge dq with a length dl. So this one is dl with a charge equal dq. dq equal lambda dl. And this value can be substituted in the total equation E. So in this case, E equal K lambda dl divided by r square. Okay. Now the second case, we have the area A. We have A. Before, in the first case here, in the first case, you see this dq in this case. dq, if you move dq, if you move dq, you can cover all the length of the object. So you must choose a small dq, we can say dl, in order to cover, to integrate this dq and to get the total length L. In the second case, we have the area A. So we have to choose a small portion, a small elements, in order that the integration of this element will cover all the area. This element can be like this. This element has dq, and also it has area equal dA. Okay? If you move this tiny element like this, you will cover all the area, as you see. So the equation, if Q equal sigma A, so dQ equal sigma delta A. So in this case, E equal K integral dQ equal sigma delta A divided by the distance square. In the third case, we have a sphere with a total charge equal Q and total volume equal to V. What is the shape? The tiny elements, the small element can be taken if we integrate this small element, we'll get the total volume of the object. It will be a shell. A shell, it's like a football. For example, we have a football here. Okay, the football is empty inside. We can choose an empty football like this. This one is a football, has a small thickness. If we have another football bigger and bigger and bigger and bigger, we can cover all the area of the object. So, okay, we can talk about the application later. Now just I want to explain how you can take dq, how you can substitute dq. Okay? Q equal rho times V. dq, this football, this object has dq charge. Okay? And dv volume, small volume. So dq equal rho dv. The equation will be E equal K integral rho dv divided by r square in the direction of r. That's all about the equations of the continuous charge distribution. In the next videos, we can talk about the application of these equations. Thank you.